Thank you so much. 皆さん、こんにちは。日本語はちょっと難しいですから、英語でお話します。よろしくお願いします。So, thank you very much, Professor Sakaguchi, for the kind invitation to speak here. Also, thanks to Tohoku Forum for creativity for this wonderful chance to speak here at the Sendai University. I thought of speaking about two topics, two inverse problems, X-ray tomography and electrical impedance tomography. They are both aiming to see what is inside some physical body, maybe a human being or another body, with a bit different probing energies, here X-rays, here electrical currents. And this one is a linear inverse problem, and this one is a nonlinear inverse problem. They have some similarities, but of course this is much more difficult because of the nonlinearity. So there I will discuss two different approaches for the solution, some optimization using Gauss-Newton methods, and then a partial differential equation based, so-called complex geometrical solution. Why is not on? Yes, sorry. Better? Okay. So, let me start. So, the first part of the talk will be about X-ray tomography, which is a linear inverse problem. Let me also mention that I represent the Finnish Center of Excellence in Inverse Problems Research. So Finland is located here in the northern part of Europe. This is the map of Finland, and we try to cover Finland with research groups on inverse problems. So we just got from the Academy of Finland, we got another 8 years funding starting next year. So we will keep inverse problem as a central topic in Finnish science for a long time. A couple of words of my background, which is maybe a bit unusual for a university professor on mathematics. After my PhD, I started working at Instrumentarium Imaging Company that made X-ray machines for doctors, so medical imaging devices. After a couple of years, I did a postdoctoral period at Gumma University with my host, Professor Ikehata, also here. That was a wonderful time of my life, living in Japan, learning about Japanese culture and food. Then I returned to Finland, and GE, the American company, had bought Instrumentarium. So for a while I worked in the American company, and then they sold some part of the company making dental X-ray machines. So I worked there, but then I returned to academic world, first in Tampere and later in Helsinki. There I am a professor of industrial mathematics, so I'm always interested in connections between mathematics and real world and technology. And also with me is part of our team from University of Helsinki, Tatjana Buba, who is an expert on X-ray tomography, Min Mak, and electrical impedance tomography scholar and postdoc in our department, Zenit Purisha, she is also working on X-ray imaging, and Janne Tamminen, also an electrical impedance tomography expert. So they will also help in the computational part of this course, because we will have some MATLAB computational sessions after the lectures. Okay, so let's go to the actual topic, X-ray tomography. So let me first give you a little idea what is going on in X-ray tomography imaging. This is a video we made at the University of Helsinki. There was also my previous student Andreas Hauptmann, he's in London now, Tatjana is here, Juho is finishing his master's thesis. So in our X-ray lab, we made this kind of experiment. We took a piece of lotus root, of course you recognize, important part of Asian food culture. Then we chose different materials. Pencil, it has carbon inside. Chalk, mathematicians of course love chalk, so it has calcium. little stones, and also from matches we took sulfur. So from the periodic table of elements, we have different atomic weight for these materials. So then we put it to our X-ray device. There's the camera behind, a Japanese Hamamatsu camera. Here's the X-ray source. And then this is what we collect as data. We see through the whole thing. And then we choose a level here and do a two-dimensional tomography. This is the so-called sinogram. A bit later I will explain in more detail how the sinogram is made. And here is some fancy visualization of the so-called filtered back projection, which is kind of the most used tomographic method in practice these days, although I will talk a little bit about a little bit different methods here, but also I will mention that one. All right. So let's go to the beginning, which goes back to Wilhelm Conrad Röntgen. He got the first ever Nobel Prize in physics for finding out X-rays. This is his wife's hand, one of the very first X-ray images. Later, these two researchers got Nobel Prizes for developing tomographic X-ray imaging, Hounsfield and Cormack. Hounsfield was working in the basement of the EMI company, which actually published music, for example, the Beatles. So that's why the record company had so much money that they could afford some engineer playing with X-rays in the basement. So he found out this is one of the early images made by Hounsfield. Of course, there's also the result of Johann Radon from 1917, where he proved that a function of two variables can be recovered from the knowledge of all integrals of that function along one-dimensional lines in the plane. So it was kind of the predecessor of the idea behind tomography, although it took really like more than 50 years for that idea to get to practice. I think as a professor of industrial mathematics, I try to promote faster transfer of mathematical ideas from research to technology. So, just to give you an idea, the X-ray tomography is used every day in hospitals. Doctors do CT scans all the time. So here, for example, is a liver. It's kind of a sad case. You see these dark things here are cancer. Anyway, the doctor can see and know what is the situation. Also, three-dimensional visualizations can be made. Here's also a kind of a problem in the bones. Some fracture has appeared here. But these are really important tools for doctors, and a lot of these scans are made all over the world every day. So let's see what kind of mathematics is behind this kind of imaging. So let's start with a very basic demonstration of what happens when an X-ray enters material. The intensity of the X-ray will go down inside the material, so the initial intensity is bigger than the final intensity. And there is a precise law for this, called the Beer-Lambert law. In this case, it takes a very simple form because I chose homogeneous material. So this homogeneous material has a characteristic number mu. It's called the X-ray attenuation coefficient. It's a positive number. It's positive because if it was negative, then the X-rays would get stronger inside the material. This is not possible. So it will always just get weaker. So there's a positive attenuation coefficient, and S is here the width of our object. So quite simple exponential decay. I will also show you the same thing for 2. Two pieces, 2 exponential decays happen. So then when we do practical measurements with X-rays, like in my lab or in every CT machine around the world, what happens is that the X-ray source sends some number of photons. This is the intensity, the number of photons sent along the ray. So in this very ideal picture, I have here a detector that counts how many photons come to each pixel. So in this case, all of the photons come through. Then, in this case, I chose the width of this block so that exactly half will be attenuated inside. So only half come through. And because of the exponential law, what happens here is that here we have 500 left and then 250 left. So now we need to calibrate the data. So we take a logarithm of these intensities and then we subtract these numbers from the empty space measurement. Because the line integral along this line should be 0. So we subtract these numbers from 6.9. So here we get 0. Here we get something in some mysterious physical units, but we don't need to care about the units because the point is that here we have something and here we have double that something, 0.7, 1.4. So this is what we have to do when we take the photographs out of our X-ray camera and want to move to line integral data. Of course, in reality, objects are not homogeneous, and actually it is much more interesting to image non-homogeneous objects. Homogeneous ones we would know already that they are just the same color inside. In this case, the Bayer-Lambert law takes this form, so it's an integral from A to B, integrating a function fx along a line, and the fx is now the attenuation coefficient inside the physical body, and then it can change point by point. Also, a couple of computations show that we have this one. So, for example, in Radon's theorem, we assume we know such line integrals, and this is the measurement world. The initial intensity I0 we can know by calibrating our measurement device, measuring the empty picture, and then I1, this is what we get from our X-ray image. So here is something that we can measure with our device, and on this side is the mathematical concept of a line integral. So then the situation looks kind of like this. X-ray is traveling inside, the integral is gathering more and more value, the X-ray is kind of measuring how much material there is, and also how, the material can also have different strengths of attenuation, different thicknesses. So the end product is kind of a measurement how much there is. This is what Hounsfield did with his original machine in the 70s. He did such a linear movement like that, collecting a profile of the object, and then he rotated the whole thing. Here I'm not showing every sweep, so there has to be a sweep for every direction. And this way, taking all of these profiles and collecting them as columns in a matrix builds up the so-called sinogram. A parallel beam geometry sinogram. So just to give you an idea how this looks in practice, so that was kind of the first generation CT machines with the parallel beam and scanning. It's quite slow to make the scan, turn a little bit, make the scan. These days it's really not like that. So the patient is put into a machine that looks like this, and then inside the machine what happens, it's actually quite, you see this is really heavy. The whole thing is really, really heavy, and it rotates at high speed, and it collects a lot of data in a spiral geometry. The patient is just pushed through, and this measures in a spiral geometry. It's very fast these days. So this is, I think, 4th generation scanner. So that's the medical practice, how it's done. And just to give you an idea, what is this filtered back projection? This is actually how Johan Radon's original formula looks like when you use it to reconstruct. But all of this was kind of just an introduction, because that's something that's well known already, used all the time around the world. There is not so much new that one can do there. I think the technology is really good, gives high resolution images, and it's really in a good shape. So what is mathematically currently a very active area of research is tomography with very few data points. Because sometimes it's quite interesting if our starting point is only a few X-ray images. Not like I showed in the geometry that you take steps like 1 degree or even less and collect a lot of data. Of course, you will get a very precise image with high resolution, but also you will give quite a lot of X-rays to the patient. And you know they are unhealthy. It's ionizing radiation, it causes cancer. So it's better to give as little as possible to people, especially if the disease is not so dangerous. I mean, of course, if there's really like a cancer or something, maybe it's ethically worth it to give the CT radiation dose. But if it's just like a dental implant or some kind of a simple trouble, then ethically the doctor should give only a little amount of X-rays. So what can we see from that? If we have just not so many images, then the mathematics becomes a bit different. I'll show you in what way. So now actually, instead of the radon transform type of imaging where we actually in the radon transform world we think of really continuous angles and continuous measurements. In practice, the world is very discrete, especially with few data tomography when we have just few directions. So let me explain this with an extremely simple example that you see here. This is a two-dimensional patient, square-shaped, and the patient has 9 internal organs that are homogeneous inside and also square-shaped. Then, if we let an X-ray pass through the patient, after the calibration I showed you, and assuming that the side of one square is 1, then actually we will measure 1 times 4 plus 1 times 4 plus 1 times 5. So we get row sum of this matrix. So if we think of this horizontal X-ray with image with 3 pixels, we get these numbers. Then we can rotate our very rudimentary CT machine, and we get vertical images, so column sums of the matrix, and then diagonals where, as courtesy to the great Pythagoras of ancient Greece, I will add here square root of 2, because my X-rays are going along the diagonals. So in this case, in this very simple example, this is the direct problem. In inverse problems, we always have a direct problem that's easy and an inverse problem that's more difficult. In this case, the direct problem is this. If we know these numbers inside, it is very easy for us to compute what these numbers should be. But this is the inverse problem. This is what we get in practice. We can take the X-ray images, and then it's like a Sudoku problem. Fill in suitable numbers so that they fit the boundary measurements, and that will be the image. But inverse problems, they are often more difficult than they look like first. For example, here, if we think about this few data tomography I mentioned, of course in this case this is very simple, so instead of these 3 directions measurements, if we have only these 2, so then we already in this simple case we face some problems because we have 9 unknowns and only 6 linear equations connecting them. So from basic linear algebra we know that there's an infinite number of solutions for this one. So it's a big non-uniqueness. Let me analyze this a little bit. Let's get into this problem a bit more closely and write a little linear mathematical model. So this is the model for the direct problem. And because this is a linear situation, we have a linear matrix equation. So we give names to the unknown pixels, up to F9 in this case. and we give also names to the measurements we have. So we have 6 measurements, 9 unknowns. F is a vector in R9. The measurement vector is in R6. And we write this kind of a model where, well, epsilon is random noise that we always have in practical situations. But the matrix A, what is that? Now pay attention, because later today in the MATLAB session, we will all construct this matrix and study it a little bit more. So this is the matrix A, and how is it done? It's again quite simple. Let's see, for example, measurement 1 is the first row here that corresponds to M1. So what happens with M1, it goes through pixels 2 and 6, and the path length is square root of 2. So we have here, otherwise they are zeros, but element 2 and element 6 have square root of 2. This is how the matrix is built, and this is really how tomography can be done. So tomography is, the direct model of tomography is really this simple. Of course, in practice there are much more pixels, or in 3D case there are much more voxels. But in the core of the problem, this is what happens. So then, because of basic linear algebra, there needs to be more than one solution. So for example, here are a couple of other patients that give exactly the same data. So there is non-uniqueness in this inverse problem. Well, we could argue, for example, that this is not possible because there's a negative value. It would mean that X-rays get stronger in this area, which is not possible physically. Well, also here, I don't know, maybe we would know that this is just too high, that there shouldn't be anything so highly attenuating. But I mean, we need a systematic way of finding the correct solution, or at least an approximation to the correct solution, instead of just guessing and ruling out one by one. So we could try, for example, using the least squares approach. So in linear matrix equations, there's a so-called least square solution if this f tilde, when we measure how good measurements would A f tilde, how close is A times f tilde to our measurement. So, and if this error in the measurement equals the minimal error, then we say that this is a least square solution. And there may be many, sometimes there are many least square solutions, a full subspace of them. Then we just take the shortest one, and that's called the minimum norm solution. And it's well known that the minimum norm solution can be computed by this very neat and beautiful formula involving also the transpose of the A matrix. So we could compute the minimum norm solution. Here it is. You can easily check that, okay, it gives the correct values, but again, it has some negative pixel values, so this is not such a good solution for our inverse problem. In X-ray tomography, it's always a good idea to enforce non-negativity, because that's something we really know about the unknown. And this is an example of the thinking in inverse problems. The measurement information in inverse problems is always somehow not enough. Even if there is uniqueness, there is instability in inverse problems, in ill-posed inverse problems. So it's, for reconstruction, it's really never enough to just have the measurement data. We always have to have some a priori information about the unknown that we combine with the measurement data to give a so-called regularized solution. It's not always so easy to find good a priori information, but in X-ray tomography, we know at least that non-negativity should hold. So that's a simple, easy piece of a priori information. So we can also use the machinery of non-negative minimum norm solution. This will give us actually this solution. And it's still not the same one than here. So clearly, even this a priori information is not enough for us. So we used here non-negativity, and we chose the shortest least square solution, which
which is non-negative. So, but it doesn't give still us a good solution, although this problem is so simple. So now let's look at a bit more complicated example. So I constructed this kind of computational phantom. So this is just created in the computer. So it has the letters CT, so we can see how well can we recover those letters. I put here attenuation value of 0.44, here 0.16, and here the same. And outside the area is just 0. So this is our computational phantom. We can try out things a little bit with it. So at this point, this is really a function of two variables, so really function defined on R2. But for computational purposes, when we want to reconstruct something, it has to be something finite. And the typical way of doing it is if the measurement is done for an object in this domain of R2, so this is a very schematic picture of X-ray positions in these 5 positions, and this is the detector. For the computational solution of the inverse problem, we need to build a forward model. And in the forward model, we divide this area where the unknown thing is, we divide it into pixels and think that inside the pixel, the value is homogeneous, and the problem is just to find the best values inside the pixels. But how many should we take? There is no rule for it. We can freely choose as many as we want. It may make sense not to take too small pixels compared to our detector pixels, although there are actually some reasons why it could also make sense, including working on convergence proofs or understanding the solution on the continuous limit. In that kind of cases, it actually may be a good idea to even use very high resolution grids. But such a choice has to be made, and now in my computational example, I will just choose to study the measurement and reconstruction in a 32 by 32 grid. So let's see how does the measurement matrix look like when our unknown is like this. So it has 1024 unknown values in the pixels. So now I choose a parallel beam geometry with not so many angles. And here I'm building up the matrix. So I'm only showing the non-zero elements of our measurement matrix. So this matrix is really, what I do here is really the same thing than we did here. So this kind of matrix, I'm just showing the blue dot is everywhere where there's something else than 0. And of course, this matrix is much bigger than 6 times 9. This is 735 times 1024. So each direction, when I turn this, it gives this kind of structured block of information there. So we go around. So we take, I think, 15 directions, and we get a matrix like this. So now we can start. This is already a bit more serious model, a bit more realistic model, although it's only, the resolution looks only like this, but still already we can see something. And now let me at this point remind you of this interesting theorem published, well, already Cormac knew this, but it's stated in a fun way in this paper by Smith, Solomon, and Wagner from 1977. It says that if we have a finite number of X-ray data, we know nothing. The proof works really in R2, in the continuous setting. And what happens there is they take a finite number of directions, but in each direction they take a continuum of X-rays. But still you can construct, it's not even a very difficult, you can construct a function that gives a 0 measurement for all of these fixed, finite number of fixed directions. In this sense, so there's always some ghosts or things you can't see with this measurement. Now this is an example of the interplay between practical finite dimensional models and mathematical thinking in Euclidean space. Because it's not actually this bad. We can actually see stuff. So this is kind of too pessimistic. I'll get back to that in a minute. But let's first see that there's something strange going on with our model. I'm now applying the minimum norm solution formula. So the same formula we saw before, and we got, well, a wrong answer, but rather reasonable. This, I would say, is not reasonable at all, especially because our value should be between 0 and 0.44, and the reconstruction has something like 10 to the power 14. So this really blows. This is just garbage. There is nothing useful in this one. But this is a perfectly good formula. I mean, this is the classical least squares theory. What's going on? Also, we can use the non-negatively constrained. Well, the maximum value is now more reasonable, so between 0 and 2.3, but we can't see anything from this picture either, so this is also quite rubbish. So something is, so what's the problem? How can this be? Well, the answer is that because we are dealing with an ill-posed inverse problem. That's the thing. Then we have bad instability. One way of seeing this instability is to consider, these are exactly now the kind of ghosts that this theorem was referring to. The theorem was in the continuum and saying that we can't see anything. Now in practice, in this case, with the pixel-based images, this is how the ghosts look like, because the original thing at this resolution and this guy, they give almost the same measurement. The difference between this one and this one, so this number, I subtracted these ones and I compared the difference to the norm of this one. So you see, it's less than 1% difference in the data, although these are much more different than 1%. These are quite different. And there are more. I can take another one. This is another one. Again, less than 1% difference in the data. So this is the ill-posedness in inverse problems. Very different objects give almost the same data. And because the data anyway has noise, random errors given by the measurement device. So, I mean, what we get from the measurement device, it's only accurate up to some number. So there can easily be like 1% random noise. So there's no way, no way to tell between these two. So now, let's now look at a more quantitative way of seeing what's going on. The basic tool here is the singular value decomposition for matrices, which says that any matrix of any size, just any matrix, can be written in this form, where both U and V are just orthogonal transformations of space, and between is D, and D is a diagonal matrix like this. We have here non-negative singular values, or let me be more precise, these are ordered from the largest to the smallest. They are non-negative, so some of them can be 0, but let me call by R the last one that's really actually positive. Of course, for the 0 matrix, these are all 0, and that's fine. Then R is 0. But otherwise, let's see all the singular values up to here that they are really positive, and then we may have some zeros, which just means that our matrix A has some kernel. So that can always be done. It's done by taking A transpose A matrix and looking at its eigenvalues. That's how this is done. And now, the thing is that, of course, one problem is non-unique. Like we saw in our small problem, there was non-uniqueness. Too many variables and too few equations. So then it's just this kind of thing that we have kernel. But there's another problem which is maybe more serious. Namely that these singular values, so that the last one here is very, very small, many orders of magnitude smaller than the first one. Then it's kind of okay, the matrix mathematically has an r-dimensional range, but it's very unstable because these become so small. This is what happens in our example with just linear tomography we did. So this is the matrix we constructed for this 32 by 32 problem. Now I compute the singular value decomposition, and here you can see the singular value. They start with something like, so here is 1, so it's a bit more than 1. Then there's a bunch of kind of nice size singular values up to here, and then they go down. This is a logarithmic scale node, so they go down like this. They don't drop directly to 0, which would be just rank deficient or having a kernel. That's not the case here. They are just going down like this, and they span, you see, they span so many orders of magnitude. This is where the ill-posedness comes from. And that's why we need a regularization method which fights that kind of instability that comes from the singular values. And like you saw, I mean, these totally reasonable solution methods, they completely blow up here. It's just not working. So something more needs to be done. Regularization was developed to deal with ill-posed problems, ill-posed inverse problems, where ill-posedness comes from the definition by Jacques Adamard. Actually, Jacques Adamard defined the well-posed problem, which means that there has to be at least one solution, and actually only one solution, and then the output of the system should depend continuously on the input of the system. And this is always the case with the forward problem in inverse problems. The forward problem is nice. I mean, forward problem is going from F to M. Oh, it's completely nicely continuous and all. I mean, everything is fine because from F to M, it's nicely defined. But the inverse problem is given M, find F. And this one actually can fail in all of these three. Maybe the third one is the most difficult case, but often it fails in all three. So for linear case, so now we are dealing with this part 1 with the linear problems. There, because we have a matrix for the forward problem, we can analyze everything that's happening very easily, because for matrices we can just see that a matrix, so it maps Rn to Rk. So this is a schematical picture of what's going on. So if A has some kernel, so this may be a problem of non-uniqueness. I mean, if A has kernel, then we can add an element of the kernel to any solution and it will not change the measurement. Also, if A just maps into this range, and there is some dimensions left over in the target space, so this is the co-kernel. So if our data is there, and often because of the measurement noise, it can be, even if the ideal data is here, the noise can throw it outside the range, so then we have a problem with existence of a solution. And then, of course, it looks like this is fine. These dimensions, they just map bijectively here, but we just saw that the singular values can go to 0 with spanning many orders of magnitude. So it means that even this bijection here is not so nice. It can be very unstable. So what we saw before, I showed the least squares, or the minimum norm solution for our problem. Here you see why did it fail. It's defined, so this is one way to define the minimum norm solution using the Moore-Penrose pseudo-inverse, where you just write kind of an inverse for A by putting here. So I mean, if A is an invertible square matrix and we have this, in that case we could just write the inverse of A, so that it would be B transpose D inverse. No. Like this. pseudo-inverse can be done for any matrix. It's done like this. If there is kernel, we just don't divide by 0. We go up to here with 1 over the singular value. But now if there is the problem with Adamad's third condition, the problem that this dr is really much smaller than d1, then what happens here, this will be a very big number compared to this one. And it will blow up any noise there is in the data. That's why we failed in the example. So what can we do for it? Well, the most classical approach is the so-called Tikhonov regularization, where by the great insight of Andrei Tikhonov, we write a penalty functional like this. So the first term here is penalizing for the wrong measurement. So if some vector f, when we apply the direct model and get simulated measurements, and we compare to the actual measurements. So if this error vector here is very large, then the norm is very large, and there will be a big penalty from not satisfying the data or not giving the right kind of data. This part is just penalizing for the size of f. So a little bit like we looked for the shortest least square solution, a little bit same idea that we give another penalty for the size of f. And now this alpha is a positive number here, which gives a balance between how much are we requiring each one. So if alpha is 0, then we are only looking at the error in the measurement, and we saw that fails. We saw that the least square solutions blow up in that case. And if alpha goes to infinity, then we are really putting a lot of weight on this part of the penalty, but then the result just has to be 0. I mean, it just goes to 0 if alpha goes to infinity. So there's a kind of a balance problem of finding a good alpha. It's a big problem in the field of inverse and ill-posed problems. There are many methods suggested, and for a given application, some of the methods may work, but some of them usually don't work. So it's quite an interesting topic of research, how to choose the best alpha. But right now, let's not go too much into that. It's a really deep question. So we are looking for the vector f that gives the minimal value to this penalty for a given alpha. So we define this kind of regularization operator parameterized by alpha and taking as argument the measurement m. This is Tikhonov regularization. Some computations can be done that show that one way of implementing the Tikhonov regularization is done very similarly to the formula we saw before. So in the spirit of this one, or the spirit of pseudo inverse of Moore and Penrose, but actually then the alpha also appears here. And this formula on the diagonal is fine even for the 0. Even if this is 0, it doesn't matter, then it just becomes 0. So this is actually one formula how to do Tikhonov regularization. With a little variational argument, you can also see that this is another way of computing it. This matrix will be always invertible because of the identity here, and then you can apply it to here. So this is a way to do a regularized reconstruction. So here I computed the minimum of this penalty functional. This is something we can try in our MATLAB session with some examples. So this is, but no positivity constraint or non-negativity constraint. This is just a Tikhonov solution. And well, I cheated a little bit and tried many values of alpha to find which one gives the smallest error compared to the real thing. Of course, in practice, we wouldn't have the real thing. That's what we are after. So that's why it's a difficult thing to choose alpha. But here, I just chose the one that gives the smallest error, and we can take the error down to 12%. Then we can add the non-negativity constraint, and then the error drops a little bit down, so it's only 10 anymore, so it's again a bit closer. to the real thing, and well, much better than the minimum known solutions we tried before. We can see something from here. And then there's a whole bunch of methods based on the concept of sparsity, which is quite a fashionable topic. It has been, like in compressed sensing, it has been around for a while. It's a very powerful technology for computing reconstructions. Let me try to explain the idea behind sparsity in very simple terms. So let's think that we have a whole subspace of vectors that give as well all equally good data fit. And then if we want to choose the smallest in the usual Euclidean norm, we would choose this one. And even if there is some noise and we perturb a little bit, it will be a close by point in this line that we get. Then, if we use L1 norm, something magical happens. Well, not so magical, it's very clear mathematically what happens. But anyway, so again, if we have these points here that give the same data fit, and we want to take the shortest one in the L1 norm. So it will be this one, and even if I perturb this a little bit, it will be the same one. Only after I really go over this point, then it jumps here. But even it's kind of robust over little perturbations. Of course, it may move a little bit up and down here along the y-axis, but that's really the point here. That's why the word sparsity, because you see the corner points have one of the coordinates 0. And in higher dimensions, this means that the solution always, apart from some possibilities of measure 0, so in typical cases, it's a corner point of that kind of diamond shape, and then a bunch of the coordinates will have value 0. And that's sparsity. In a big vector, in an infinite vector, sparsity means that only a finite number of coordinates are non-zero. That's a precise mathematical definition. In computational practice, it's more vague. It's like, let's say, most of the elements in the vector are 0, and there are only a few, only sparsely non-zero elements in the solution vector. So it's quite a powerful, this leads to quite powerful methods for reconstruction. And one of the methods is called total variation regularization. There, this was introduced by Rubin, Osher, and Fatemi in 1992 in the context of image denoising. In that context, it produces images that have homogeneous areas of the same gray value, with the boundaries between those areas being as short as possible. That's why it's sometimes called lasso, kind of tightening around areas as short as possible. In the computational things we will do in the course, we will use this so-called anisotropic total variation. By anisotropy, I refer to thinking of the gradient of a function which is in two-dimensional cases. So this is a vector in R2, and now we can think about the length of the gradient in P norms also. So this would be the 1 norm. We just use the sum of the 1 norms. So in the case of images, this is just simply differences between horizontal neighbor images and differences between vertical neighboring pixels. Also, there are other possibilities because this kind of thing leads to minimizing functionals that are not differentiable, which causes sometimes trouble for minimization algorithms that are based on a differentiation. So another possibility is also to round off the absolute value function in such a way which is asymptotically the absolute value function, but this beta thing here kind of rounds it around the origin. That's another option, but this is really more faithful to the original idea of penalizing the first derivative with an L1 norm. So now when we apply total variation, so positivity constraint or non-negativity constraint, this is the data fit term or data discrepancy, and now we use the gradient of F1 norm and the anisotropic norm for the length of the gradient, like I just showed. So we get this picture, and the error goes down to 7%, even lower, because for our phantom is kind of piecewise constant, so then total variation is a good approach for it. It would show better for a larger resolution, but we can do that in the computational examples. So here we already looked at 3 different regularizations that have clearly different properties. So the thing is that the data discrepancy stays the same, and we use different a priori information. Here, this actually kind of promotes smooth images that don't have really big jumps anywhere. This does the same, including the positivity constraint, and total variation with non-negativity constraint favors piecewise constant areas of X-ray attenuation. Of course, there are many others, but these are somehow, I think, the basic story. This is the most classical one, a bit more complicated, and then this already takes us to the modern field of sparsity. So then let's see for fun how this looks like for a real target. So not anymore computational target, but a real target. We made it out of cheese. This is slice imaging after all, you know. So let me show you. This is Tatiana cutting the cheese. She also showed great handicraft in cutting the letters. Well, I think we found out that cheese is not the optimal material for this, but we will prepare more, but it was a fun project anyway. So our CT cheese is there rotating again. You can see even some holes in the inside the cheese. We get the sinogram, and then this is applying Radon's original formula. It has kind of a sharp feeling to it, but also it has many artifacts all around the place, this kind of line artifact, because we are using only so few directions, and filtered back projection is not really designed for few directions. It's not so good in that case. This is the positivity constraint or non-negativity constraint Tikhonov, and this is total variation. And also for this dataset and also the Lotus dataset, they are openly available on the Finnish Inverse Problem Society webpage. We want to enable all researchers to try this kind of things with really measured data. And also, in case if some of you really likes this stuff and gets into this stuff, you are really very welcome to visit us in Helsinki. We can measure your favorite object and you get the data. It's really an idea to get theoretical mathematicians also try out new ideas with actual data. It's not so difficult. Well, it was quite difficult to put everything up, but now it's done, so it's easy. Also, a mention about the total variation approach. Our group in Finland, we did this in collaboration with a company. I will tell a bit more later. I'm happy to report that we were actually the first to try it for really measured X-ray data in 2003. After that, there are many papers. There's the Chicago group and the Copenhagen group, and now there's really lots of papers. It's really a good and nice methodology for X-rays. Also, I must mention that the way I'm computing these total variation things in the computational method, it's quite not the most sophisticated, not nearly. I'm using something quite simple. I want to also state that it's a really active area of research how to compute efficiently these total variation minimizers. And there's a whole industry of extremely good groups making more and more faster and better methods. A while ago, still, I think the split Bregman iteration was leading. I'm not sure what is the best one now. But also, Tatjana is an expert in these kind of optimization methods, so she has some really good information about these things. So you can ask her. The way I'm doing it is using this kind of trick I learned from Teemu Pennanen, who is an optimization professor in London. He said that with a very basic, in optimization field, it's a very basic little change that can change our L2 and L1 norm combination into a quadratic problem in standard form, although including some inequality and equality constraints. But this is a standard form, so what I'm using is just, in MATLAB there's a basic command called quadprog that can just solve problems like this. So my strategy is just to rewrite this in a bit different way so we can achieve the standard way and then use it. So the way to do it is this. For any function, we can actually divide the function into positive part and negative part, which is kind of a nice, very simple trick for if you have a function that has some positive values and some negative values here and there, we want to write it in this kind of form, function plus part and minus part, both non-negative. So the plus part would follow the function when it's positive, and then it's 0 here, and then again like this. So this would be the u plus part, and then the negative part, the same thing here, it follows the function, and here it's just 0. But this is with a minus sign. So this is a very simple idea, splitting up the function in that way. And what is nice about it, then actually the L1 norm of the vector, so we are of course talking about discrete vectors in this case, so like sample functions. So then the L1 norm is just the sum of all of these elements in the non-negative u plus and u minus. So it's just an inner product with the vector full of elements 1. So then we can write, so we lose something of course when writing the problem like this. We get inequality constraints and equality constraints, and the problem dimension goes from, because f is in Rn, and these guys are, well, depending on the boundary values, but close to Rn anyway. So it's 5 times more dimension, which in optimization is always bad news if you have to optimize in a higher dimension. It's more difficult. But on the other hand, we get rid of the 1 norm, so that's a plus. So this is something we can try in the computational part, how to do this. So then I want to make a remark about what is back projection, also filtered back projection, because actually in the end of the electrical impedance tomography, I would like to report some very new results on how actually even the nonlinear diffuse tomography with electric currents is related to the X-ray tomography filtered back projection. So as you remember, we saw in many places already with the minimum norm solution, we already saw the transpose of the system matrix or the direct problem matrix appearing. Let's take a look, what is it? So our direct problem matrix takes an image in Rn, well, of course, the image is a two-dimensional array of pixels, but we just name them with one index, so we think of it as a vector in R. And of course, you should organize the pixels in the 2D way to understand what A is doing. So anyway, A maps a vector in F into Rk, which is the sinogram space. A transpose maps from the sinogram space back to the image space. How should we think about what is the intuition, or what is the modeling feature? What is A transpose doing? So if we look at A, how it maps one point into a sinogram, this is how it looks like. That's why sinogram is called the sinogram, because this looks like a sine function. So this happens with the forward matrix A. So what happens if we apply the transpose? We see this kind of an image, and the way to think about A transpose is that it will sum all X-rays going through the point in question. That's the back approach. Back means back to this point. It just adds all the lines that are in the measured directions we have. So it maps them back into the image space. That's the back projection. We can see it also in another way. If I put one point in the sinogram space, and we see how does it look like? Well, it looks like one of our X-rays. Another one, there, it's another X-ray, or of course quite coarsely approximated X-ray. But here you can see these gray values here show those numbers we saw, these ones and square root of 2's in the very simple example. But this is how the back projection works. And now there is also the connection, if we briefly go back to the continuous case, like the filtered back projection and radon transform thinking way. So radon transform is usually parameterized like this. So there's a function f, which is, let's say, a compactly supported non-negative function in the plane. Its radon transform Rf depends on two parameters. The angular direction parameter, and S is the direction along an X-ray. So theta defines a direction, and actually the X-rays go perpendicular to that direction, and S tells how far is this X-ray from the origin. So it's a way of parameterizing all the lines in the plane. So then it integrates f along this line, or this is another way of writing it. But so this is the X-ray along which the integral is taken. And then I personally like this derivation the most. There are many derivations for the filtered back projection formula. Somehow I like this one. So, like we saw that the back projection matrix took the X-rays that go through a given point. So if we think like that, so if we want to reconstruct the unknown function f at a fixed point, so then the pieces of data that are the most related to that point are in the integrals along lines that pass through that point. It's kind of an intuitive idea. So if we take all that data, we sum all that data together in this case, meaning that we integrate over the directions from 0 to pi. So these are the line integrals from minus infinity to infinity with t, and we integrate from 0 to pi all the lines going through the point. Well, we can also multiply and divide by t and move to polar coordinates. So this is from 0 to 2 pi. So actually, then when we move back to Euclidean coordinates, we see that it's actually a convolution between f and 1 over length of y, which I can write, well, I can write it in the way of convolution. So actually the back projection operator in the continuous case is a convolution with this kind of singular, weakly singular kernel. So then we know from distribution theory what is the Fourier transform of 1 over length of y. It's 1 over length of xi in the Fourier space. So then we can introduce the Calderon operator lambda that works by taking the Fourier transform of the function, multiply it by length of xi, and then inverse Fourier transform. So it's a kind of a pseudo differential operator. It's almost like a derivative of order 1, but it's a pseudo derivative anyway. So then from the convolution formula we see that if we integrate all the information to the point, so apply this back projection operator on the Fourier side, it looks like this actually. So if we want to counteract this operation, we need to multiply by length of the psi vector. So then this means that actually it holds that f equals Calderon operator times the t operator. So that's identity. Calderon times this t operator. But another way of thinking about this t operator, which if we go back here, so t operator is just integrating. Well, there are the line integrals, but also this operator integrates over the directions. So kind of this is the Radon transform part, and then this is the back projection part. So this is another way of writing this. So this is a maybe not quite the adjoint operator, but this is a dual operator of the Radon transform in a specific sense, which can be checked from Natterer's book. But the point here is that this is what the hospital machines use, this kind of filtered back projection, where there is a Radon transform computed at very small angular steps, so it's almost kind of like continuous data. And then, so this is the data coming from the machine, RF. This is the back projection, and this is the filter. So that's the filtered back projection, where that comes from. So this was a very brief introduction. I'm happy to discuss the more details if someone wants, but this was just kind of a very quick explanation. So then I would like to draw your attention to an even more difficult problem called limited angle tomography. Of course, it's also a linear inverse problem, but it's already much more difficult than the full angle sparse problem. Let me show you why. So in this case, we construct the sinogram so that our measurement angles they don't go the full half, so they only go, let's say, halfway. We don't have the whole thing, only to halfway. So then our matrix is kind of like just part of the matrix we had before. Again, we can compute the singular values. Here in gray are the previous ones for the full matrix that went all around the object. And now that we only have kind of half around the object, the singular values go down a bit even sooner. Here, the problem doesn't look so much bigger, really. They are almost on top of each other, but there is a significant difference related to the wavefront set, which is wavefront set takes into account the singularities in the function, but also the directions where the singularities are. And that's actually why I chose these very round kind of letters from the Cooper black font, that they show nicely, they have quite a nice wavefront set that can be easily analyzed. They don't have any sharp corners. So now if you look at these papers by Alan Greenleaf and Günther Ullmann, the classic paper of 1989. Then this is also a very nice paper, very, I think, easily approachable, well-written paper, 93. And we also combined with Jürgen Frickel and Todd Quinto some recent works on it. Highly recommended papers explaining why in the limited angle data we can only see part of the wavefront set in a stable way in the data. So what happens is actually, so this I call the stable part, and there the thing is that for the stable part, so for example, why is this point stable? It is because we have this X-ray in our data that goes through the point and is tangent to this jump curve, and also we have plus minus epsilon angles. If we have that in the data, then we know this part of the wavefront set. But then, because our limiter, so we have vertical, and we have this data, but we don't have this at all. So we don't have it, so that's actually in the unstable part. So there's a quite neat characterization of what parts of singularities we can expect to see from the data alone. Of course, in any case, we need a priori information, even in the full angle case, but here even more so, and for these red guys, we need some serious a priori information because the data is saying nothing about them. So that's why limited angle tomography is much more difficult. So this is just the filtered back projection. And you can pretty much see that these parts that are on the blue here, you can see them. The other ones, not at all. If we try the other methods, oh well, I think I only have here the total variation. Pretty much the same thing. I mean, it does a better job of seeing where there is nothing and where there is something. But these parts, well, it's pretty much these places that can be seen. But this can also be used to an advantage. We know that the reconstruction will be poor here, but in some situations, maybe this is all we need, these parts. And that's something I would like to give you an example about. This is one of, well, let me say, this is, in my scientific career, this is the work I'm most proud of. I really, I'm happy that we could make this thing go all the way to practice, and this really is not my work only. There are really many people who worked on this problem. We worked together, well, with Instrumentarium, where I worked after my PhD, and then GE bought it, and then they sold this dental imaging part. But with these companies, and especially then with this dental imaging company, we developed the following product. So think about this situation when a tooth is missing. And you know, this can happen to anyone. You don't have to be a boxer or ice hockey player to lose a tooth. My friend Pasi, in his 50s, he went to the dentist, and the dentist just said that we have to remove this tooth. And he said, please, don't remove it. I like that one. But the dentist said, I have to remove it, otherwise soon you will have very serious problems. So it just has to be removed. But then, you know, these days, what happens is they put a dental implant, a fake tooth, so to speak. And I'm sorry for this gross picture. I made it black and white, so it's a little bit less gross than the original. But obviously for this guy, the situation is very serious. But the idea is that in this place, the dentist will put such a titanium screw, and then a tooth implant is fitted on top of this titanium screw. This one has to be very sturdy in place. So the dentist needs to drill a hole here to make a good place for the titanium screw. But you see here is a nerve. So there is a tunnel inside the bone. Here, actually, there's some nerves are coming out at some point here. If you are the adventurous type, you can try and find. There's one place here that hurts more than other places if you massage it. That's the place where the nerve comes out. So here, when you drill, the drilling should be deep to make the implant sturdy. but not too deep, because if this nerve gets damaged, there will be chronic pain in the face or maybe some paralysis, expensive lawsuit for the dentist, really bad. So the dentist wants to avoid, make it as deep as possible, but not too deep. So what we did at the company was actually the company history of Palodex dates back to Yrjö Paatero, who was a professor at University of Helsinki working on dental X-ray imaging, and he developed this so-called panoramic dental imaging machine. This is from one of his patents about it. So the thing is that this kind of machine rotates around the head, and with some ingenious geometric idea, the picture just picks out a sharp layer inside the dental arc. Let me show you. So here is my PhD student Maria Rantala, who works at the company. So she's using the machine. It goes around the head like that, collects data, and you get a picture like this, where you see all the teeth at the same time. And actually a dentist can see a lot of things in this kind of, there is a sinus, and there is the end of the jawbone, the TMJ, and all kinds of things can be seen from this image. But it has geometric distortion. Because of the geometric movement of the machine, for example, the vertical part of the image is fan beam geometry, and the horizontal part is parallel beam geometry. And it's somehow distorted, so it's really not good for measuring the precise millimeters for drilling the hole. So it's not good for that. Another interesting thing about the machine is that there is an X-ray source, and this detector is very narrow, so it's like 2000 pixels high, but only 64 pixels wide. So it's really like a slit like this. So it cannot take like a square image. It can only take a very narrow image. So what we did with the machine is we programmed a new movement for it. So it makes a scanning movement. It rotates and makes a scan like that with the very narrow detector. So then it can collect like a two-dimensional image with just a narrow slit detector. But it cannot go all around. You saw how tight the space was around my head. So it cannot do this kind of movement all around the head. Necessarily there is such a limited angle. So what we could do with the machine was we could put it total angle of view 40 degrees, which is very low. Actually, it's already very severely ill-posed problem, such a limited angle tomography. It takes 1 megapixel images that look like this. So this is from a dry skull, these pictures. It takes 11 images, and the unknown voxel space, the doctors, they would like to see something like a 1/100th of a millimeter, maybe 1/10th of a millimeter is still okay, but the resolution shouldn't be worse than that. So we end up, like we saw in the beginning, my Sudoku problem, with 9 unknown numbers and 6 measurements. In this case, we have a 3-dimensional voxel Sudoku, where there are 7 million voxels unknown, and there are 11 million data points, but from a limited angle of view. So that's quite the same. At the core, it's the same kind of problem, but much bigger scale, and also the limited angle trouble is there. However, with using the total variation approach and some other approaches, of course, with practical machines, there's a lot of programming and problem solving to do, but such inversion methods are in the core of the product. It has been in the market from 2008, and there are thousands of them all around the world, and so many people have enjoyed the possibility of getting much less radiation. Namely, here is an example of, so this is a navigation slide showing it what part is the picture taken. So this is with a cone beam CT, so dental dedicated device that actually it's a big machine, an expensive one. So a dental clinic has to they need to buy an expensive machine, to get such a high resolution as here. So it's really great. This is very detailed and high resolution. But it's not needed for this purpose. Actually, what the doctor needs, or the dentist, just to see, okay, here is the top, this is the top of the root channel, and here is the top. So how many millimeters is this one? It can be as well seen from this one, and this they can do with the machine they already have at the clinic. The panoramic image, panoramic machine, every dental clinic has. It's a basic machine. They already have it, and we just reprogram new movement and put in some inverse problems, mathematics. So it's kind of a software upgrade that makes it produce this kind of images. And this one gave 100 times more radiation than this one. So this is how mathematics, the inverse problems mathematics, can make a difference in real life. I mean, really related to the health of people. So that's why I'm really happy about this work. Yes. So then a couple of words. The stuff I'm talking about this course is pretty much covered in my book with Jennifer, and we have all the MATLAB codes related to the book. So some of the MATLAB codes I'm showing here, but you can also find all of the rest if you want to work with them. Also, I mentioned that there are these X-ray datasets. They are in a very easy to use format. You will see in the MATLAB sessions, we give the data and we give the matrix and some instructions. And also, we already also made some basic regularization methods. So you can really take some real X-ray data of some objects, like the lotus and the cheese and a couple of others, and try out these methods very easily. Also, I want to mention the work of a Dutch and Belgian group. Mostly I've been working with Joost Battenburg, but there's a whole group, of course, working with this. They made a so-called Astra toolbox that provides these forward projection and back projection algorithms in three-dimensional and really high-dimensional cases. So, because what we do here in the MATLAB, we have to do with quite a small resolution because of computer memory and computation time. But when people want to go to really bigger problems and more practical problems, then it's a free software for having those implementations. Also, Per Christian Hansen, who works in the Danish Technical University, his team has built very nice total variation solvers for regularization. So there's also possible to use them. So these days, you know, with the internet and open data and open software, there are many possibilities like this to test mathematical ideas. Also, if you get interested into this kind of X-ray tomography thing, here is a list of books that are related to this topic. So there are many. They're all a little bit different. This is a very practical and physics style, and I think this one and this one are quite theoretical, and these ones are between those extremes, and so there's a lot of selection. And I think I will stop today's lecture here. Thank you very much.